This is video 17 in our series Topics in Tensor Analysis. In this video, we want to introduce the concept of Christoffel symbols. And a reminder that the playlist for all the videos is featured at the website digital-university.org. Okay, to help get us started here, let's review an old graphic where here we have a set of curvilinear coordinates u1, u2, and u3, and here are Cartesian coordinates x1, x2, and x3 with their respective unit vectors, and here is a point P in space with a position vector r. And what we had discussed in the previous videos is that at each point in space that's located with one of these curvilinear coordinates, we can form a tangential vector to each of these coordinates at that particular point in space. So here's point P, and for the u1 axis, here's a vector that's tangent to it at that point. For the u2 axis, here's a vector that's tangent to it at that point. And for the u3 axis, there's a vector that's tangent to it at that point. And the way that we obtained these tangential vectors was taking the partial derivative of r with respect to u1 to get this, or with respect to u2 to obtain this, or with respect to u3 to obtain this. Now, in order to do that, this is our general expression for r. Then, of course, we would have to know how u1, u2, and u3 can be expressed in terms of x1, x2, x3, and vice versa. How to express these in terms of the u curvilinear system. And we have a specific example of that with spherical coordinates. Now, these spherical coordinates differ from our other curvilinear coordinates because for spherical coordinates, the position vector itself, or more rather, the magnitude of it, is one of the curvilinear coordinates, along, of course, with theta and psi. And we know how to express x1 in terms of the spherical coordinates, and for x2 and for x3. So each one of these is a different function of r, theta, and psi. And likewise, for here, the position vector r can be written like this. This is a unit vector on one of the Cartesian axes, another unit vector, or we could just write as I, j, and k. We've written it like this before. It can be written like this. You, of course, see it different ways in different books. For this video, we'll go ahead and use these symbols. Well, x1, that is some function of u1, u2, and u3. x2 is a different function, and x3 is yet a different function of u1, u2, and u3. Just like for here, x1 was a certain function of r, theta, and psi. x2 is a different function, and x3 was yet a different function. We're saying the same thing here, only we're writing it in more general terms. So that means then that r, our position vector, can be written like this. This is x1, this is x2, this is x3. And then so each one of the tangential vectors just is derived from this general formula. Now, these tangential vectors that we can create like that, they're not unit vectors. and we didn't try to construct them as unit vectors because in most textbooks they don't do that. But the point then is that any vector or any tensor that is in this curvilinear coordinate system can be written like this, with its contravariant components along E1, E2, E3, and add them up. So the E1s, E2s, and E3s, even though they're not unit vectors, they do call them basis vectors. Now what we want to consider is something fairly simple. What happens if we take the derivatives of the basis vectors? For example, going back to spherical coordinates, here is the position vector r. We can write it like this. This is x1, x2, and x3. This is a unit vector on the Cartesian system, another unit vector, a third unit vector. And for spherical coordinates, we can get the tangential coordinates er, e theta, and e psi just by taking the partial derivatives of r with respect to small r, or theta, or psi. And that's, of course, is how these were obtained. Well, here, if we wanted to, we could take another derivative of this with respect to either theta or psi. We could take another derivative here if we wanted to. And we could take another derivative here if we wanted to. And it's taking the derivatives of these tangential or basis vectors, taking the second derivative of them, that's what gets us into the notion of Christoffel symbols. So here then is a position vector r written in terms, this would be the x1, this would be x2, this would be x3, and we said the tangential vectors or the basis vectors are just the partial derivatives of the position vector r with respect to any one of these u1, u2s, or u3s. We just designate it with respect to ui, where I can be 1, 2, or 3. So specifically then we could say, well, ei, just to take a moment and write this out, that would be equal to then the partial of this with respect to ui plus the partial of this with respect to ui plus the partial of this. With respect to ui. And that indeed, that's how we got these different tangential vectors, or these different basis vectors. So far we haven't done anything new. Well, as we just said here, when we were looking at the spherical coordinates, if we wanted to, once we have these tangential vectors, here, here, and here, if we wanted to, we could go ahead and take another derivative of them. If we did that, if we took, say, the partial of this with respect to theta, that will just give us another vector again. If we took a partial of this with a second derivative, say with respect to psi, that would just give us another vector. Well, here, let's just write it out, what we have here now, in more general terms. We're going to take the partial derivative of this say with respect to uj. So that would just simply be with respect to uj, with respect to ui. Same thing for these components, nothing new here. And finally, for our last term, second derivative, like this, where, of course, I and j can have values 1, 2, or 3. These i's and j's have nothing to do with the expression for our Cartesian unit vectors. Okay, so here we had a tangential vector, and we took the derivative of it. And what did we get? Another vector. Okay, well now, any vector that we have in this curvilinear coordinate system, as we said, can be expressed like this. So this new vector, or we can write this more succinctly like this, where k is a repeated index, so it can take on values 1, then 2, and 3. We sum over the repeated index. Well, that means then that this new vector that we made by taking the partial derivative of the basis vectors, that's going to be a vector that we can express in terms of the basis vectors. So we could just say then that this is going to be what? Well, we could just write it, say, as theta k ek. Specifically now, of course, we are considering expressing components with respect to these basis vectors that by definition is contravariant components. We, of course, have gone over that in previous videos. So we have an uppercase contravariant components. But typically, this, we could write it like this, but the way it's written is like this, actually. This vector that we can write as a combination of the basis vectors. Any vector in this curvilinear system can be written as a combination of its components along, as its contravariant components along the basis vectors. This is a vector. This is the basis vectors, so we can write this as the combination or the sum of its contravariant components with respect to each basis vector. But this is not usually how it is written. Instead, it's written like this, with a gamma, a k, ek, but then we have these symbols here, I and j, and we include these. And this is the Christoffel symbol. So really we can think of it as the Christoffel symbol is representing here the vector that we make when we take a partial derivative of one of the basis vectors, that this then is one of the components of it with respect to the tangential basis vectors that we have in our curvilinear system. Now, remember I think it was in video 8 and 9 when we discussed reciprocal basis, where we had, say, EI dot EJ equals this. So we're here, let's take the dot product of both sides of the equation with respect to this. So on this side of the equation, we're going to have the partial of EI with respect to UJ dot partial, we wrote this wrong, this dot EK will equal dot EK. And this, of course, is just delta KK. This is just simply 1. Remember, going back to here, this is 0 if I does not equal j. It is 1 when I equals k. Or this is 1 when I and j are the same. When I equals j, that's 1. If they differ, then it's 0. Well, these are the same. Therefore, this is always 1. Therefore, this is always 1. So we can just take this right out. And that tells us then specifically this Christoffel symbol, we can find its value by taking this type of dot product. And we need to have our K up here. Okay, so again, what we were doing is that we realized that a position vector, we can express it in terms of the curvilinear components. With the Cartesian unit vectors, and we can take the partial derivatives of this with respect to any one of the Cartesian axes, like you saw us do with the spherical coordinates. That gives us the tangential vectors in the curvilinear system. Then we took the partial derivative of this with respect to one of the curvilinear. We took a second derivative to get this expression that just simply gave us another vector. Well, this vector that's in the curvilinear system, just like this vector, can be written as the sum of its contravariant components along these different tangential basis vectors. And that's what we have here. This is the repeated index. However, we also include these other indexes here, and that's what gives us the Christoffel symbol. And then this, we can find out specifically what it is by taking this dot product. Now, notice that if we are in three-dimensional space, then we would have exactly 3 tangential vectors. So k would take on values 1, 2, and 3, and so would I and j, because I and j just simply refer to the curvilinear coordinates, and there are 3 of them. So this can take on values 1, 2, or 3. This can take on values 1, 2, or 3, and so can that. So this Christoffel symbol, when we're in three-dimensional space, can have 27 different components to it. Let's just get rid of the whiteboard. Here's our Christoffel symbol here. Now, let's say that k equals 1. Keep these constants, so now we have this. Get this in better focus. Okay, here's our Christoffel symbol. Let's say k equals 1 and we keep these constant. So now we have 3. Now let's work with this one. I can be 1, 2, or 3. So now we have these, and then for each one of these, j can be 1, 2, or 3. So we take this one, j is 1, j is 2, j is 3. And now for here, j can be 1, 2, or 3. And for here, j can be 1, 2, or 3. So this ended up giving us 9 different expressions. Of course, this will do the same, and this will do the same. So in three-dimensional space, each point has 27 different components. And again, we'll deal in the next video with more properties of the Christoffel symbol, specifically how it relates to the metric tensor. So come back and join us for that video, and we'll continue along with our discussion.